All right, today we are going to build on what we talked about last time, and today talk about inscribed angles of circles. So last time, just to review, we talked about central angles and their intercepted arc. Though we didn't really call it an intercepted arc. So right here, if I was looking at, say, the center here, we talked about again last time, okay, pretend that's a center. And we said that if we have like a sprinkler or something here and we were to rotate it through, let's say, 50 degrees, then we would have, again, something that looked like this. It was a central angle because it was located at the center of the circle. And then we said when you rotate something like that, you create essentially an arc here. This arc, we said, has the same measure in degrees as that central angle. Now, we didn't talk a lot about arc length. We'll do that in the future. So recognize we're not saying it has the same arc length. It is just the same measure there. When we pull that angle back, and we pull it all the way back to the circle, so something like this is what we call an inscribed angle. So an inscribed angle is an angle, and again, that gives you a definition here. They intersect on the inside of the circle, so this is being pulled back all the way to the circle. This guy right here, he would be considered an inscribed angle. Now, obviously, it doesn't have exactly the same angle measure there. It's creating the same arc if you look at those ends that are meeting there. But what I want you to notice is if you were standing here at the center of the circle, this is kind of like when you're sitting on the front row at a theater. You don't like that spot because your head has to turn a lot to be able to see the left side of the screen to the right side of the screen. If you're sitting back here on the back row, you don't have to turn your head as much, right? You can see a larger horizon or from left to right than you can if you're up close. So this angle is actually smaller than that central angle, and the relationship there and the key takeaway today that we're using is that this inscribed angle is actually going to be half of that central angle. So if the central angle, again, is 50 degrees, then if we were to pull that angle all the way back, it's going to be half of that. I'm going to show you this on this applet to maybe make some sense of this. So we talked about, again, that central angle, and again, right, we can move this around. It can become very large. This would create a major arc on the outside here. This would, 180 degrees is like the semicircle, and then any of these are creating a little minor arc of CD. Now, again, we can show the arc and its measure out there, and we talked about that they're always the same. Those central angle and that arc measure are going to be the same. That's the relationship there. Now today, if we pull that back, this is our inscribed angle. Now notice that inscribed angle is half the measurement of the central angle. And no matter where I move this, notice that it's not changing that central angle. It is staying half no matter where it's moved. So that central angle, if you notice, the key is to look at where those chords are meeting, and if they're meeting at those same points and creating that same arc, then we know that that relationship is going to hold. And one of the curious things we'll look at today is when this gets all the way to that central angle becomes 180, you've actually created a nice little right triangle over here, and I can't get it to exactly 180, but if we could, we would see a nice little right angle thing appear there. So that's the idea today. Central angle, same measure as the arc. When we pull it all the way back, that inscribed angle is going to be half the measure. So I'm just going to go through some examples. Essentially, those are the two properties that you're looking at today. Again, this guy in here, he's the inscribed angle, right? Just to kind of review. This one on the inside, that's the central angle that you're looking at there. And then this out here, the arc that they're creating, that's what we call the intercepted arc. And a lot of times they'll say this angle is subtending the arc. Or in other words, the arc is being subtended by an angle. To use that terminology. So here's our little theorem. Again, it's on page 598 if you're going to look through your book. And you'll notice if this guy out here, right, is equal to a value of x, then this one pulled all the way back here, angle B, is going to be 1/2 of whatever x was. So let's just look at a few examples. These aren't overly complicated. You're just going to need to throw in some algebra here or there to use some of it. but it is a property that we need to be able to recognize in relation to circles. So on number 1 example, again, arc AC right here, right, is 100 degrees, which means that this intercepted arc back here would be half of that. So in this case, x would be equal to 50 degrees. Okay. Again, looking at this one, the arc out here is 120 degrees, which means that the intercepted arc would be half of that. So this piece in here, we know that this little 3x minus 3 needs to be equal to half of 120. Half of 120 would be 60 degrees. So we know that this needs to equal 60 degrees. Then we could solve that. We add 3 to both sides. That leaves us with 3x is equal to 63. Go ahead and divide by 3, and x in this case would be equal to 21. So we can find the value of x there. Looking at number 3, again, this one is just important that you recognize when there's more than one angle thrown in there, recognize the chords that they're subtending. So even though there's all these different shapes going on, notice that this guy right here, this angle, so figure out what chords are making up him. The arc that he's subtending, or his intercepted arc, is this guy. So again, if that's 71 degrees, that arc on the outside has to be double that. So if we take 71 and we multiply it by 2, we know that this guy out here is 142 degrees. So we're figuring out, well, what would x be? Well, if 4x minus 6 needs to equal 142, then we just solve by adding 6. We get 148 when we add that, and then we take 148 and we divide that by 4, and that gives us 37. So we can figure it out that way. Number 4 is also curious to kind of look at. This one's putting in a couple triangles and intercepted arc, relating it to the central angle. You'll notice here the central angle, and this is what I want you to notice. We've got to understand both relationships to get to where we want. Notice this is what we want to find is x. Well, it doesn't even extend necessarily out to the circle there. So we just need to find a roundabout way and use what we know about our geometric shapes to find this. So here we're given a central angle of 50 degrees. Now remember, the central angle matches the degree measure of the arc that it creates or subtends. So we're looking at this arc right here. Notice that angle C is the inscribed angle, creating that same intercepted arc. So again, remember, the inscribed angle is half of the measure of the central angle or the arc. So this guy back here is 25 degrees. Now this is a really important thing that we recognize. Here is a triangle inside the circle. And you might ask, 25 degrees, well, how does that help me find the other one? 2 ways you can do this. Some of you might be saying, oh, well, these two make a straight line. So if that one's 50 degrees, then this guy, he must be 130 degrees because that has to add to 180. Now we know 2 of the angles inside of this, so we can take 180 and we can subtract those other 2. That's an absolutely great way to do it. The other way you can think about it, that erased a lot, is this is 25 degrees here. This is an isosceles triangle because this is a radius of the circle and so is this. And remember, in an isosceles triangle, if these two side lengths are the same, that means that the angle measures of these base angles are also the same. So if that one's 25 degrees, then we actually know that x is also 25 degrees. So a couple different ways you can think about that one. Now the rest of these theorems just are building on what we just talked about. So this first one, the theorem is called inscribed angles of a circle theorem. It's just saying that if you have 2 that intercept the same arc, 2 angles, they're going to be equal. So we kind of already looked at this one up here on example 3, where we were pulling out a specific angle. All it's saying is if we were to look at this guy right here, so here's an angle, this angle, right, that we're seeing is creating this arc out here. Notice that this angle clear over here, he's creating that same exact arc. So this kind of, remember that app we looked at, if we move that intercepted arc, it doesn't matter where it is on the circle, If it's creating the same arc, then it's going to be equivalent. So in this case, if we know that these angles have to be the same, we can set them equal to each other. And then we solve. So let's move the x's to one side. So that gives me 6x minus 3x. And then I'm going to move my 11, so I'm going to add 11 so that I end up with 18 here. Then divide by 3, and x must be equal to 6 in this case. Okay. Again, another one says that if a right triangle is put inside of a circle, then the hypotenuse must be a diameter. So we kind of already looked at this one as well. Just notice if your central angle is ever 180 degrees. So if that's a diameter there, then this guy is half of that, which is 90 degrees. So always looking for diameters, because that relates to the angle of 90 degrees. All right, let's do a few more examples of these. These are similar to ones you're going to see on your homework. Once we put the inscribed angle into a polygon. So this is called an inscribed quadrilateral, right? It has 4 sides, quadrilateral. And we are inscribing it inside of a circle. In other words, each of the vertices of the quadrilateral are on the inside of a circle, but actually meeting at points on that circle. So that's what we call inscribed. And this theorem right here is saying that any quadrilateral inscribed in a circle has opposite angles, right? Opposite meaning across from each other, that are supplementary. And remember, supplementary means that they're going to add to 180 degrees. I'm going to show you why, and then that's just either we can understand the why or we need to kind of memorize that property there. So let's look at number 6 and talk about why. Now notice, again, these are just inscribed angles. So if I'm looking at specifically, and it's easiest maybe if you draw these in just when you're doing your assignments and things, but there's an angle right there of 80 degrees. Notice, and I'm going to ignore kind of all the other pieces just so I can make sense of this arc out here that it's creating, now that whole arc, not just a piece of it, is double that inscribed angle. So if that's 80 degrees, then this whole arc out here is 160 degrees. Now, if that's the case, remember these are circles, so if that's 160 degrees, then this other huge arc out here must be the rest of that 360 circular degree. So if the blue piece is 160 degrees arc, then a 360 minus that 160 leaves 200 degrees out here for the red arc. Now, if that's 200 degrees, notice that this angle now over here, that's meeting here at these endpoints, is creating the red arc. So if the red arc is 200, then that inscribed angle there would be half of 200, which would be 100 degrees. This is why, because those two angles that are opposite each other, they create the whole circle when it comes to the arcs. So their angle measures are 180 degrees in total. So again, if I know that this is 85, then I know that its opposite angle has to be 180 degrees minus 85. So if we take 180 and we subtract 85, then x must be equal to 95 degrees. Now again, that's the y. That's where it comes from. Sorry, not the y variable, the y reason. That's where it comes from, but really we can just use that property over and over if we recognize those opposite angles are going to be supplementary. So let's look at the next one. Again, number 7, you're given that this is 93 degrees, so this one's pretty easy to calculate. The z is going to be 180 minus 93 degrees, which would be equal to, again, z, and that means that z, right, if we take 180 and we subtract 93, would be equal to 87 degrees. That one's not bad. Notice your x and y. I don't know either of those, so to say that they add to 180 doesn't really help me, unless I realize that, notice this arc, okay, maybe. Notice that this angle is the one creating this arc out here. And it looks like they gave us the measures of those arcs. So we've got a 58 degrees and a 106. If we add those together, we add 58 plus 106, we get 164. So we know that this whole arc measure out here is 164 degrees, which means that x, the inscribed angle, is going to be half of that. So x must be 82 degrees. Again, not as much calculation on that as it is just understanding those theorems and being able to connect that geometrically. Now if x is 82 degrees, we know that y is supplementary of that, so 180 subtract 82 degrees would give me 98 degrees there. Okay, again, these other two just maybe a little more challenging examples algebraically. I'm just going to work through them to kind of show you how this goes. Again, sometimes in geometry we get lazy because we think we can just stare at the picture and then identify the angle measures or arc lengths, things like that. But we're going to apply what we know about algebra to help us out here. So again, here we go. We've got 105. We know that these two need to add to 180. And again, when you say that in your head, they need to add to 180, just create an equation where they add to equal 180. So we do 105, and we do plus 7x plus 1. They need to equal 180. Now you're saying, what about the other two? We'll worry about them in a minute. So we just combine like terms. We've got 105 plus 1, that's 106. We subtract the 106 to the other side. So 7x is equal to 74. And if we take 74 and divide that 7, that actually gives us a decimal of about 10.6. Okay, so again, we're setting them equal. I'm going to zoom a little bit. I know it's annoying on the video. Okay, then we would just do the other pieces. So notice again, this one has a y in it, this one has a y in it. That makes those pretty nice. They would also add to 180. Now it's tempting to say, oh, they would be equal, but remember, opposite angles add to 180. So we combine like terms. We've got 4y and 7y. So let's combine that to give us 11y, and then we've got 14 plus 1 and 180 on this side. Subtract 11y and 15. Oh, that's a mistake. Don't do that. Take it back. Okay, subtract the 15. Yeah, don't move the y. And then we get 11y is equal to 165. And that gets rid of our 15 there. And if you divide that, y is going to be equal to 15. Okay. So again, opposite angles add to 180. Create yourself a little equation. Number 9 is very similar to the last one. First of all, I want you to notice that it looks kind of like A and B is a diameter. But if the center of the circle is not drawn on that line, so notice if it doesn't look like that, then you cannot assume that that's the center or the diameter of the circle. The center in this circle probably would be over here a little bit further. So we're not making any assumptions there, but again, we've got a polygon inscribed inside of here, so we know that opposite angles, these guys are going to add to 180. So I could say, well, 24y plus 4x needs to equal 180, right? Notice that, sorry, that doesn't look like an x. There's an x and a y in that equation. It's not super helpful, but if I also notice that 9y plus 14x is equal to 180, now I have a system of equations. Two unknown variables, but I have two equations, so we can use substitution to solve. We could use elimination. It might be a little crazy of a graph, but you could graph this and see where those cross, and that would also give you your solutions, those intersections. So I'm going to use substitution, and the reason being is I think that this 4 is going to allow x to be pretty easy to solve for. So if I take just this bottom equation, and I'm going to take, so 24y plus 4x, and in substitution, remember we want to get a variable by itself, so I'm going to subtract the 24y over to this side. Now those aren't like terms, the 180 and 24y, So I'm just going to have 180 minus 24y over there. And again, I'm trying to get x by itself, so I'm going to divide by 4. And if I divide something by 4, I have to divide every piece by 4. So when we do that, we get x is equal to 180 divided by 4, which is 45, minus 24 divided by 4, which is 6y. Again, substitution says once I figure out what x is equal to, I shouldn't box that, that looks like an answer. Then I just take this up and I actually plug it into the other equation for x, because that's what, again, x is equal to. So we would do 9y plus 14, and then whatever the x is that I found, I'm going to put right in there. So here comes my 45 minus 6y, and that's equal to 180, just that original equation. Then it's a matter of solving. Once you've figured out what system you're going to use. Oh, look at all the colors. So we multiply here, 14 times 45. I guess I should write 9y. And we get 630. Then we do 14 times 6. So we keep distributing. And we get negative 84y. We start to combine like terms. So it looks like I have a 9y and a negative 84y. That creates a negative 75y on the left side. And while we're at it, let's just move this guy to the other side of the equal sign. So if we take 180 and we subtract 630, we end up with negative 450. And then again, we're just solving, so we divide by negative 75. And we end up with negative 6, oops, not negative 6, positive 6. Excellent. So we've got a y value. Then you just need to find the x value. So again, remember, once we figure out one of them, you can just jump back up and use one of the original equations. So if I want to use like this first one, this guy, then I would do 9. Oh, I know what y is because it's 6 plus 14x equals 180. And then I just continue to solve. So 9 times 6 is 54. I subtract the 54, and I end up looking at 180 minus 54. Yes, I'm using a calculator. 126, and then I divide that by 14, so x is equal to 9. Now again, I use substitution. If you want to use elimination, you can. The important thing, though, is that you can set this up geometrically. We understand that the relationship between the opposite angles on the inscribed polygon add to 180, and then we do need to be able to apply our algebraic pieces and knowledge to solve that. Again, the 3 takeaways from this one, making sure we understand the central angle is equal, right, to the arc measure. When we pull that back, then that inscribed angle is half of that. And again, no matter where that is, right, that's still 25 degrees. That's still 25 degrees as long as it's intercepting that same arc, okay? And you're going to practice with that. On this next video, I'm just going to go through a bunch of examples. You can watch through that next video. It'll give you practice examples like you'll see on your homework as well as your quiz. Or you could give your homework a shot and then come back if you need help.